Okay, so good afternoon, everyone, and welcome to our icon seminar. Because today we really have a special speaker who has done excellent work in learning and control. This is the first seminar for Icon's themed seminar series on learning meets control. So each semester we have a theme. Last semester is the human autonomy teaming. Again, welcome to Icon events. And Icon was launched a year and a half ago with the aim of enhancing collaboration on research and teaching to address fundamental challenges on autonomous and connected systems. So learning, obviously, and control are important parts for autonomous systems. That's why we established this series of seminars on learning for control. And actually today we have invited a distinguished researcher in the field who has done leading work in this area. But I will leave the introduction about the speaker to our two new faculties, Fazil and Masha, and they are the seminar organizers of Icon's seminar series this spring. So Masha.
Thank you, Shaoshai. Yeah, it's our pleasure to have Professor Nali here to kick off this seminar series. Professor Nali is the Gordon Mackay Professor in Electrical Engineering and Applied Mathematics at Harvard University. She received her BS degree in mathematics from Zhejiang University and her PhD in control and dynamical systems from Caltech. She was a postdoctoral associate at MIT. And her research lies in control, learning, and optimization of network systems, including theory development, algorithm design, and applications to real-world cyber-physical societal systems. She has received numerous awards, including NSF Career Award, AFSR Young Investigator Award, ONR Young Investigator Award, Donald P. Ekman Award, and McDonald Mentoring Award. Yeah, with that, I'm gonna let Lina start her talk. Yeah, thank you.
Great. Thank you, Shaoshai, and thank you, Masha, for the introduction, and thank you for your invitation. I visited Purdue 3 years ago and had a great time talking with everyone. So that's why I even feel come back, return to a family. So it's my great pleasure to come back to share some of our recent work on learning and control and centering around Zeroth-Order method. Before the talk, I'd like to thank all the students and postdocs who have contributed to this work. Yujie, Yinyin, Xing, Runyu, Zhaolian, and Yang. So in particular, Yinyin is actually interviewing Purdue right now. So it's a good opportunity for me to share some of her other research that she didn't have time to cover during her talk. So also feel free to ask me any question during the talk. I hope to have a more interactive discussion rather than to finishing my slides. Let me do a very high level of the motivation. So in the past decade, we have seen an explosion of data. So taking the photos as an example, this is the earliest photo taken in 1827. The growth of the photography was slow till the end of the last century. So with the digital camera, especially our cell phones, we have seen a boom in the number of photos. So here is a famous ImageNet, and here is a snapshot from my cell phone. And you can see that I take too many repetitive photos for my kids, and I do not want to delete any of them, which can provide a great database for people to recognize kids' face expression. So now with the explosion of the photos, we have seen a revolution of learning methods in the past decade. And once the deep learning has outperformed humans in the image recognition, the deep learning is almost everywhere. Besides the image data, there is an explosion of other types of data, for instance, the IoT data. So our society has more and more smart devices which are capable of sensing, communication, computation, and actuation. So with this data and with the devices, so we start visualizing smart house, smart manufacturing, smart transportation, and smart and personalized healthcare. Indeed, there have been many exciting news. Here is an example of Boston Dynamics. We have seen many cool videos from Atlas almost every year, and how Atlas is capable to perform tasks that I would never imagine that I'm able to do. But we can also easily find videos how Atlas fails. And this is actually from same-sided robot doing similar tasks. So now speaking of the societal system that are closer to our daily life, the situation is even more cruel. Earlier last year, so there was a big unexpected winter storm in Texas. To cope with the winter storm, the ERCOT had to perform rolling blackout. So millions of people's lives got affected. And then for autonomous driving, it is actually devastating to watch the tragedy news of the car crashes. The message is that like learning for physical, societal, dynamical system is very, very challenging. To address these challenges, there has been a growing need in both sides, like in integrating machine learning and dynamical control. So learning is very powerful in image recognition and language processing, and control has been very useful of handling physical dynamics. So there has been many, many successful stories in both sides. On the theoretical side, learning has been focusing on developing algorithms to achieve good convergence speed, sample complexity, like have a good nonlinear regret, statistical guarantee, or how can we generalize the result, the generalization. So on the control side, people have been focusing on how can we guarantee the system is stable, robust, and we provide the worst case guarantee rather than just statistical guarantee, and how can the systems could be integrated together and still maintain the original performance. So for the success of learning for societal dynamical system, like this agreement, I think, well, in both sides, we need to integrate learning and control, taking advantage of both sides. Well, this is not new per se. So learning and control has been interplayed in the past and now. To give you more concrete examples, I picked two types of learning problems here. The first one is supervised learning, and the second one is banded, or sometimes called as Blackbox Learning. So of course, there are many, many other learning problems as well, but let's just focus on these two. So in the supervised learning, we are interested in learning a model to predict the data given the data samples. And here the theta is a model. And typically the problem is formulated as a optimization problem, like try to find the best theta model to predict the data, making sure the prediction is close to the truth. And the L is the loss function. The method people typically going to use to solve this problem is do the stochastic gradient descent or its variant. So on the other hand, what is the banded learning? So for the banded learning, the problem is to kind of handle the unknown models, unknown functions. So for this problem, what we have a function we want to optimize, but the difficulty is we do not know the formulation of the J. So the only way we can really go ahead to evaluate is to take a data sample like the theta and waiting for the environment to return the outcome of the decision theta. So typical algorithms that people have been used or developed to solve this problem, like the Zeroth-Order optimization method, this upper confidence bound, type of sampling, and many others. So this is two standard learning methods. For the control side, like I think most the audience are from control background. Let me do a quick overview. So for the control, usually we start with dynamical system, and the dynamics here, the X state, it tells the evolution of the system under the system disturbances, measurement noise, and will return some measurement that the controller can use the measurement to take the control action to further influence the system dynamics. Right, the typical question we are interested in, like, can we design the controller to stabilize the system? Besides stability, can we achieve certain optimality, or can we guarantee robustness, adaptivity? So this is regarding the control side. And what's the challenges recent? For all the problems we've been talking or dealing with, we're trying like pushing the boundary of the control application is the system become more and more complex. And first, it's actually hard to find a model to like, what is the right dynamical model to remodel the evolution. And secondly, like even we have a roughly a model structure, typically the parameters are unknown or partially unknown. So with this guarantee, like how are we going, like people say we can use some learning methods, natural deductive learning method to help us. So the first direct way to use it, like now we think about supervised learning, what we can do is we can use the data we get from observing the system to build a model. Like that's kind of like to finding those parameters theta to do the better prediction. So in our control side, we call is system modification. And this is kind of almost similarly as a supervised learning problem. And then we can using the statistical guarantee of the conversion speed from the supervised learning to do a better system modification. So once we have a model, then we can go ahead to apply the certainty equivalence, and we can add in some robustness, like a robust variance certainty equivalence to design the control method. So what are the challenges for this one? As I mentioned before, once we're dealing with complex systems, especially you can think about, for example, healthcare system, it's actually difficult to have a model, like what is going to be the right model to start with. And even if we're going to have the model, those kind of F theta, H theta here, it's probably going to be typical people probably right now going to use in the deep neural net to model it. And we're going to end up with a very complex nonlinear system. And what the tool we have the nonlinear system, hard to know what tools can be applied. The nonlinear control is very challenging. So this is about the model-based method. We start with a model, identify the model, then go ahead with the control design. So this, like, another way that has been attracting a lot of interest recently is like using those black box learning to do it. So what does that mean? For here, like we can go ahead even without really modeling the system. Like we know this is the dynamical system in the way that there's a state that's going to be changed once I change my control and once my system has disturbances. So based on observation, I'm going to do a control policy, and I can parameterize my control policy. Right? You can do the linear parameterization or go ahead doing those neural net parameterization and twin the theta. So once I pick the control policy, I can wait to observe the outcome of the system, like figure out a way to evaluate the performance for the controller that's called like this J theta. So now you can see it's almost look like the black box learning. We can take a policy that's like the theta S now become a policy. But to evaluate the policy is like either we run simulation or you put in the policy on the real system, like waiting for a certain period, then you roughly have estimation of it. So the reason I want to highlight is, look at here, putting the J tilde and J tilde rather than the real J, is as you think about the control problem, we always have stochastics in the system. Every time when we pull on like a make a decision and wait to evaluate, it's always going to be affected by the disturbances realization. What that means, the J tilde theta can only be an estimation of the true cost function. It's never going to be the true J theta. And I will come back to this one later, right? That's actually also caused some difficulty. It's not really as clean as the standard black box learning if I can, hey, really evaluate the J theta. So this is usually right now people call that as model-free method. So what's the challenge for the model-free method? So like looks a very natural tool, a framework I can just go ahead to implement. But what about the stability? I pull and just randomly get the theta, like was the theta already crashed my system? If I really going to use the theta online in the real system, what about like overall, how the theta really going to behave, the convergence? And do I really have some of magnetic guarantee for the dynamical system? We know this is a very complex system anyway. And the other thing is, I think one major challenge is the model-based method, we start with the model, we can put in the prior knowledge. But then for the model-free method, like how are we going to really incorporate the prior knowledge? What's a good way to incorporate? So those are the challenges for the model-free method. Like I have those challenges here. I'm not going to tell you I have an answer for all those challenges. Like I think that's ultimately would need the learning and control people together, like to address all the challenges for real system. So now on the other hand, let me come back on like the other direction. So for the other direction, so when we really go into like implement those like learning-based control method into practice or using some other learning method for the real system. And then people actually will start to ask some other questions. We'll face some other challenges besides those typical learning problems, it's a guarantee, right? What about like the transient dynamics during my learning period? Because I might usually run my learning on the fly, for example. So that's come to the question about, can we even further just improve the learning method itself? Because the learning method itself will affect the transition during my learning process. So for this style, let's like look at the algorithms. The learning algorithm people always have, I think no matter what kind of method people have been talking about right now, it's always going to be iterative method. What the iterative method means is like based on the previous estimation of your model or your decision theta, and go ahead according to some learning algorithm doing the update to get in the new theta. So as a control and dynamical system person, you can immediately recognize, right? This is a dynamical system. It just have a like dynamics from the optimization algorithm. So once we recognize the connection, we actually can go ahead just treating the learning dynamics itself as a dynamical system, and we go ahead to think about, do we have any tools from the control we actually can go ahead to shape the learning dynamics? And you will see from the talk, we have a lot of things we can offer to improving the learning method. And there's a lot of like recent work already, and this is just some examples. So today's talk, well, I'm going to only focus on two perspectives that I mentioned before. So the first one is a learning for control, and I will only focus on the Zeroth-Order method. The Zeroth-Order method means I'm not going to really model the system, but definitely the structure of the system will affect the performance, and I will discuss that later, right? How the structure of the system will affect my learning performance. So for this one, as I repeat, what we're going to do is we train this at the black box, taking the data, and using the outcome of the realization from the simulation or from the real implementation to evaluate the J and to see how we can do it. And on the other hand, what I'm going to show is this. So I'm going to focus on the Zeroth-Order method, like the Blackbox Learning method. So I'm going to look at this method to think, can I even further improve the method? Because if I'm going to use the Zeroth-Order method to solve my control problem, I really want to have a better performance for this Zeroth-Order learning method. So that's kind of the focus I'm going to talk about today. If any question, feel free to stop. So give a quick preliminary about the Zeroth-Order method. So like Zeroth-Order method, I'm going to focus on is working on the differentiable function. So as I mentioned, we want to minimize the cost function J, but we don't know the structure. So that means we cannot revise the gradient. So typically what the Zeroth-Order method means is doing the gradient estimator. So the gradient estimator, let me explain what the gradient estimator really means. So the one natural way I think everyone can think about is from the gradient definition is the finite difference. So this one called the 2-point gradient estimator, what this means is I need to just one evaluation based on my current theta, and I do the perturbation. So here, I'm picking one random direction and putting some perturbation, then to evaluate the difference. Another parameter is chosen to making sure that in expectation, this is going to be roughly the true gradient. And for the perturbation, there are different ways to do the perturbation. In the learning optimization community, the two popular one, this is a Gaussian random perturbation. So for each Zi, you're just taking the Gaussian distribution. And then another one, you do the joint distribution is you're going to pick random direction from the unit sphere. So this is the 2-point estimator, but the one difficulty I mentioned, right? The J tilde is well corrupted by some like stochastic. So in practice, what is really performing look like is the finite difference approximation is really difficult to implement in reality because this stochastic is very different. So in reality, it's a single point gradient estimator. So single point estimate, what it means is we actually don't need to do the finite difference. You're just taking one point and follow this rule, we're going to get the gradient estimation. So there are lots of math behind it to say what's the expectation and what's the variance. On the high level, you can just view this gradient estimation as a stochastic gradient, but the bias is non-zero. So which is different from the stochastic gradient descent paper in the machine learning. Like typical people assume it is the unbiased estimator. This is going to be biased, but the bias will be controlled by the perturbation, the radius. So this is a preliminary. Now let's come back to give you more like concrete thing, like what exactly how we're going to use it. So I'm going to focus on two parts. So the first one is actually like Ian is the one of the first, like is one of the first author for this work. So how are we going to use those Zeroth-Order method to do the control? We actually can go ahead to directly talking about network control, which fit into the econ sim. And the second one, come back to talk about, hey, if we want to use improving the Zeroth-Order method, how can we design using control scheme to improve it? So like as a very quick recap, what's optimal control problem? We have system dynamics. We have a stage cost when people are talking about optimal control. Depending on the state, control action, there's one stage cost evaluation. And typically what people want to solve, they want to like minimize the accumulated cost. This is the discounting, or just like infinite time horizon, the limit average cost. Like you can pick any one, which is not very important for this problem. And for the optimization viewpoint, as I mentioned, we're going to parameterize it by the theta. Once we parameterize, this optimal control problem is becoming optimization problem. And the one thing we need is we would need to making sure the theta can, like with high probability, making sure the system is stable. And Zeroth-Order method, how it's going to be run. This is my controller at this peer like episode. I will run the simulation, getting a reward estimation, the cost estimation, and using the Zeroth-Order estimation, like I showed before, this is my gradient and to update. So this is like putting all the things together, how Zeroth-Order method being applied in those control problems. Feel free to ask me questions. And now let's look at like for the LQR. So why people getting excited is, So there was a pioneer paper 2018, which actually showed this method actually work for those LQR nicely. So the LQR problem is this linear dynamical system, and we have a quadratic cost. And we know for this LQR problem, the linear state feedback policy covers the optimal policy. So what this says is when I parameterize my policy, I only need to do the linear parameterization, which is done by the K here. So once I doing that, I have the cost function, I view the LQR as a optimization problem. And how to guarantee the K is stable, like mathematically, just A plus B K the eigenvalues, those probability. So when I say successful story is for this paper, like you can look at, this is the Zeroth-Order method I mentioned before, and people like by choosing the parameter in a correct way, we can guarantee stability with high probability bound, we can find the optimal global optimal. But there's a question behind it. Like for this problem, I think control field already know this is non-convex. Why this method going to work? This is like kind of even a worse version compared to gradient descent. So let's come back to the optimal optimization landscape. For the LQR problem, I'll come back to discuss more about the optimization landscape later, like to say when the learning method will work for the control. So for this type of problem, like even this is non-convex, but we have some other nice property, like the cost function is gradient dominance, and it's like, so it's guaranteed the stationary point is going to be the optimal point. So like within HighLow, right, if you haven't heard about gradient domination, which is fine. It's just like for this type of problem, it has nice property, even though it's not non-convex, and makes this work. So now let's look at like, can this one like be extendable to some more complex system? Because in reality, the LQR problem, the simplest one I showed before, is never really work for those real problems almost. So now let's look at like go beyond, like think about the like partial preserve, like the multi-agent case. So now we have a like network system. Not really need to model what is the network structure. It's just like a very big system. And we have the sensors put in a different location so they can observe some partially information of the state. So the agent's ICE control policy is limited by his observation. And for here, let's just think about static control policy, Ki times Xit. So everyone's stage cost still the same, it's quadratic, and the cost can be different, the different Qi and Ri, but everyone has their own local observation of the cost. So the goal is to find those control policy for every agent to minimize the global cost. So in the high level, like the A and B, because the complex system is a network, it's hard to know, like you really know all the components of A and BI. So we assume the A and BI is unknown. So the problem is we want to use those, like what's information for each agent? Each agent has local observation, each agent has local cost. So we want to use this information to find optimal controller. Now, how can we do it? So as I mentioned, like the Zeroth-Order method is a very nice framework. We just kind of plug in. So we plug in to see what's really happening. So in the high level, I want to find the K, but the K is parameterized by those local controller Ki. So at each time, how people are going to update the Ki is according to this rule. So I just want to highlight like the information, like this is the cost from the joint action. So what is happening is I need to have a way to evaluate the global cost. And on the other hand, when I do the perturbation, so when I evaluate this kind of the partial gradient information on my own decision, so my own decision when I do the partially like perturbation, so we have a two different perturbation rule. The Gaussian rule, it will be easy taking the Gaussian Zi, but the other one for the unit sphere, I need some coordination to making sure I'm staying in the unit sphere. So why like here I'm putting this one, if I do the perturbation R times C, if I'm making this be really Gaussian, so the worst case, or eventually with a like not zero probability, is going to be performed very bad because this can be unbounded, which is going to crush our system. So for the stability, that's a limit of our choice. We should just do the bounded perturbation and that kind of unit sphere. Let's put another question, right? They need to jointly do some joint random sample among all the agents. So that's a challenge. How can we really like handle these two challenges? So that's like where the communication going to help. Like if they cannot really communicate, it's almost hopeless to understand what's going on with the entire system. So they're going to use a local communication. How are they going to do the local communication? Now I'm going to give you the algorithm, like give you a like high level how the algorithm really work. So as I mentioned, typically for when we apply the learning method, like this kind of Zeroth-Order method, we're going to have a 2-time scale. So as a like the first time scale T, this is kind of the same T as my system dynamics T. And I call each one as episode. So during each episode, so for this slow time scale, what I'm going to do is at the beginning of each episode, I will generate like the random perturbation and figure out what the control policy I should implement to the system right now, like this for each agent. Once I apply that, then I'm going to observe what's going on with the system. And after a period of time, I'm going to use in those observations to produce an estimate of the global objective. Once I'm doing it, then other things is kind of just follow the learning method, right? I'm going to estimate my gradient according to the Zeroth-Order gradient estimator, and then I'm going to perform the gradient step. So this is the high level how the method is going to work, and you can see the 2-time scale method. And the difficulty, what's happening for here is this. So first of all, I need a global cost, as I mentioned, the challenging one. How can we guarantee like getting the global cost? So one nice thing is this. For here, since I'm waiting to evaluate the accumulation of my cost, but since I'm waiting to get in the estimate of my accumulated cost, I can also like kind of communicate with my neighbors. Like I can pass my local cost observation to my neighbors, and jointly we can estimate what is the global cost. And because the estimation is just a summation of everyone's cost. So for those people who are familiar with this consensus method, right? If we design this consensus metrics well, you're just passing around your new observation to your neighbors. Eventually, as time goes on, so my estimation will be a good estimation of the joint global cost. So that's like how the consensus scheme can be applied here. One thing I want to highlight, you can look at here, compare with like people who are familiar with the consensus optimization problem. I'm not really running the consensus on the gradient step, because for this step, for my algorithm itself, I'm actually waiting to evaluate my accumulated cost. I can use that time to just do another estimation. Like using when I'm waiting for the system running, I can also pass the cost evaluation observation to my neighbors to get in the evaluation. So compared with the single agent method, I'm not really wasting any time. This is almost the same complexity or the same time scale as the single agent case. And on the similar procedure, now for the talking about how to do the perturbation, there's another thing I want to highlight. This is another difference. Once we apply the learning method to do the control, there's learning people don't worry about it, but when we're doing the control, we actually worry about it. So this is the accumulation of the cost. And we are talking about a stability. It's like an infinite time horizon notion. And if I really want to proceed with my algorithm, I need to truncate my system simulation, or I need to truncate, like if I'm doing the real implementation, I need to kind of stop the experiment. And that stop will cause another error for this approximation. And sometimes even the system is like unstable, but then you're actually using those costs. That's making the cost be really, really high and use the cost to do the gradient estimate. That's leading to the next step, the gradient step will go in really becoming unbounded, it will hurting the stability. So for that step, when we were thinking about stability guarantee, what we did is we actually adding a truncation, right? If the cost is really, really high, then I shouldn't really trust the observation I have, because it's just like one round of experiment, which is not a very good estimate. So this is another thing that's when we apply the learning method to the control problem, like what's the point that we should pay attention, and we need to figure out a way to handle it. And another one, as I mentioned, is about the perturbation. So I said for the perturbation, running the stochastic, like the Gaussian perturbation, which like is able, when we can run the Gaussian perturbation by the individual agent, but it's very difficult to guarantee stability because ZI can become really, really large for the perturbation. So the way we're going to do it, right, for the unit sphere, we're just using this kind of simple rule. Like if I run my Gaussian perturbation, and then I just kind of divide it by the joint norm, then I got the unit sphere. And similarly, how can we really get in those joint norm? We can just run another consensus along with the way when I evaluate my cost. So putting in summary, right, this is a 2-time scale algorithm. And even for the single agent LQR had a 2-time scale as well. So what we can do, we can stuff more element into this fast time scale while we're waiting for the accumulated. We can do the global cost function evaluation. We can also do the random perturbation generalization. To generalize those random perturbation. Put them together, we can just go ahead to implement the algorithm. So like while I was introducing the algorithm, you can see we like to apply the method looks simple, but if we want to guarantee, it then become very complicated. We had those tricks to making sure the system is going to be stable. So for the performance guarantee, the first question we ask is, can we really guarantee certain stability, like even just with a high probability bound? So the first, we actually can show the procedure. So since we deal with a linear system, we have some guarantee like characterization about stability. So once we define the prudent parameter in a certain way, we guarantee the stability. And that's first, and the reason why we guarantee the stability is, as you see, like we have the bounded cost, we have a way to control our perturbation, and putting all the things together, that's the way to guarantee stability during the process. And another thing is about optimality. So the optimality is people always, like the learning people care about sample complexity. If I want to achieve certain good controller, how much sample I need? Like you look at that 2-time scale algorithm. So we want to know how much sample you really need to have until you have like roughly a good control policy. So we have a sample complexity bound, and like in the high level, it's like 1 over epsilon force, and epsilon describes the control accuracy, like the optimality of the controller. And I will come back to discuss about this later. But one thing I want to say about this performance is I will come back to talk about performance guarantee. Like this is about the gradient. What is that really happening? Like, are we really talking about optimal K, or just only saying some stationary? I will come back that in one slide. So someone would like go ahead to implement the algorithm. At the beginning, I was a little bit suspicious, right? How much data we really need to have that they're really going to work like with a real system. So this we did one simulation. Like the building control, temporal control. And it's very interesting is like when we implement the algorithm, so you look at the iteration, this is about one, here the iteration means the like slow time scale, how many episodes we need to have. So after like the 50 iteration, it's roughly already went through like the right trend. And if you just keep doing it, it's actually doing better and better pretty quickly. Actually much better than the theoretical performance guarantee we predicted in the theory. So now let's come back to discuss what do I mean when I say performance guarantee. So the stability performance guarantee, which is clear, is consistent with our control and dynamical system. And the other thing is about like the optimality guarantee we put in the paper is this notion. So this is the gradient. So what we really say is the gradient will becoming small if I keep running the learning algorithm. And the problem itself is definitely non-convex. So, and what exactly the gradient really means, according like about the real cost J, right? Can we say anything beyond the gradient? So this is actually the question we go ahead to ask ourselves. Like this is important because I really talk about the optimality of the controller. So let's compare with like the single agent case that I showed before. Like what's the difference? Why things break? So this is a centralized LQR, like the 2018 that pioneer paper. So we compare with what the guarantee. So for the stability, both of them can guarantee stability. And optimality, for this like classical testable case, we can really show the optimality is smaller. Like as we keep learning, we're getting closer and closer to the optimal K. But for the discrete LQ I was showing before, no, we only guarantee stationarity. So now about another different, like what really happening. So we look at who the band, we talk about we want the K stay in the stability region. So the single agent case is nice, just one component. For the general case, that become multiple component. Now you can imagine if I'm at different component, that's probably what already control, like tells how much optimality I can really achieve if I start initialize from some bad component. That's first bad news. And the other thing about the structure for the JK, the reason why people can show this optimality guarantee because the performance, like the gradient domination, this property. For the multi-agent case, we only had one thing, this is called coercive. What the coercive means is at least I can guarantee once my gradient, perform my gradient descent, at least my K is not really going outside the region. It's like I can guarantee stability along the line, that roughly the coercive means here. But then in terms of optimality, there's no additional guarantees, there's no gradient dominance. I cannot really say much about stationary point, it's lack of properties. So in fact, like now I'm even changing the single agent. The reason why this is happening, it's not because it's multi-agent, it's just because it's partial observation. So partial observation also measure like the bad news I'm showing here works for the single agent with partial observation. The partial observation case become very complicated, and that's motivates us to go ahead to think, right? Hey, we know for the partial observation, the static controller is not the optimal controller. So and we should have looked into the dynamical controller. So we look into dynamical controller and say, hey, can we now have a better geometry for this problem? So then for my other problem I've been talking about before, I can just do another parameterization. I'm going to parameterize my controller using dynamical controller, which is AK, BK, CK. And if this works, then I can just looking for the optimal control in this way. So when we go ahead to do it, so the good news and bad news. First of all, I mean, definitely still going to be non-convex, like the control problem is a non-convex problem, but the kinetic component become much better. It only has at most 2 kinetic component. And the kinetic component that actually has a symmetry is what it means if I start with any kind of component, it's fine. I'm not going to lose my optimality. They are symmetric to each other. And this the symmetry comes from the similarity transformation. So, but then the bad news is it's for this one, once we go into the dynamic controller, because it's similarity transformation, the problem even is not coercive. It means even your AK, like you can just keep heading to the like infinity, but the AK, BK, CK, the good composition, then you can still guarantee stability of the closed loop system. So like during the dynamical process, we cannot really guarantee stability along the learning. And they can have a many stationary point. A stationary point can be non-optimal. We find a non-strict saddle point, which are bad. Like you see all those bad news also again, kind of saying the Zeroth-Order method will fail. But the good news is we're actually able to show if we actually have like end up a stationary point, but the stationary point is observable and controllable, we actually can say that controller is global optimal. So right now, our recent work is we are really kind of based on this positive result. Can we change our like gradient method to still kind of helping us go ahead to find the global optimality, which is ongoing work. I'm not sure whether our method is going to be positive or negative eventually. So with that, any questions for the first part of work? The second part of work actually can be much quicker. Any questions? Will I wait until I finish the second part and we'll go ahead? So, okay, now I'm going to.
A quick question from me.
Okay,
yes, it's more like you just mentioned that it's a global minimum things. In CS, usually they don't care about that very much. They only care about most just drive to get equilibrium. So what is your vision?
Not really the case.
Yeah.
No, so I think in the machine learning side, it's kind of so 2 things. So first of all, so many optimization problem like the matrix completion problem. So people have been already showed this almost like here. There's no sparse stationary point. It almost means every stationary point is global optimal. So that's one reason then people trust as long as I can, like for example, jumping from the strict saddle point, then will be fine. It's like all the local minimum are global optimal. Then they're talking about saddle point. So that's one reason. And the other one is about the like equivalent or like the optimality exists. So machine learning people take care of the generalization. So they actually don't really care about too much about optimality of the problem itself. They want to know like my learner model can really generate to some other data set. And then it turns out like people were saying like the SGD is actually now going to convert to the optimal point of your original problem, but then those points has a better generalization. And then people go back to think about, hey, what's the real reason? Oh, because my SGD had some like natural regularization going on for the problem. So indeed, like the other point will be better than the global optimal. So I think that's the reason. It's not like the optimization people don't care. It's like for this kind of 2 set of problem, then those points, there are different issues. But if I really, for example, the control problem, I really want to find the controller and the controller corresponding to true cost, then we care about optimality because the cost of the like saddle point probably really means really bad performance.
Yes, yeah, exactly. Do you have any vision on, how to, get the global optimal from the just equilibrium plus simple condition?
Perturbation. So,
yes. Okay, perturbation.
I can tell you the result. What we did right now is like, so this is a parameterization of the AK, BK, CK here, right? So, and like if it's minimal realization, so everything will be fine. If it's non-minimal, that means you can do model reduction. So, and then some component is not useful. But so what we're doing, like for the component that's not useful, do the model reduction, then we actually can add additional component back, and then to perturb the system, then to making that point becoming a strict saddle point.
I see.
So if it's a strict saddle point, I can further add a random perturbation than to jumping out from the saddle point.
I see.
Yeah, but then the perturbation is not like the perturb SGD that people did in machine learning, just adding the random noise. No. So we actually need like first, like for example, do some model reduction and adding particular perturbation first, and then to add those random perturbation like the CS people doing.
All right, thank you.
Yeah, great. Yeah, great question. So it's ongoing work. I hope things work. Okay, now I'm going to give a very quick thing about like another dimension of the performance for the algorithm. Like when we're doing the zeroth-order method, I just apply them. It's kind of everything kind of given by the optimization method itself. Like this is sample complexity. So typically you can say this is a 1/epsilon false, which is typical, like which is slow. So we want to ask a question, can we do better, right? Even the interpretation with this simulation is faster than this, but that's only one simulation. So we want like theoretically, can we do better? So people always will say, okay, go ahead, do the natural. I will have one slide saying the natural method is actually not really very robust when we're talking about the sample-based method in the last slides. But let's look at, for this one, when we work on this problem, then we realize the symmetric story in control is extremely seeking control. Right, for the extremely seeking control, we do solve the problem, minimization, it has a gradient flow. But we don't know the gradient, how we're going to do it. So, and control and dynamics people like this block diagram, even though I always get confused by the block diagram. But in this case, the block diagram is very useful to redesign our machine learning method. So the block diagram for this case, like system plant, which is unknown, and like look here. So we have a state, we have perturbation from the extremely seeking control, and using the sinusoid signal to perturb it. Because sinusoid is the deterministic case signal, we can control how much perturbation we put in the system. So we're doing that, we wait on the outcome, we add another multiplication using this information as my gradient estimation. So this is the block diagram for the extremely seeking control, and putting one math sentence, it just says x dot equal this guy. And what this guy is about is when we do the averaging over the period of the sine omega t, we actually got the approximated gradient descent, x dot equal minus k gradient f. So this is extremely seeking control, and I put in the block diagram. So like how people analyzing it, because you can we have a large frequency omega, and that can do some time scale separation, kind of similar thing like what I showed you before, like we have the kind of time scale when you want to evaluate the system. Like two different time scale, and here like kind of you put in the same time scale, but they have time scale operation. Like the fast variation is to perturb the system, and the slow variation that will describe the X main evolution. So small amplitude, and how people analyze it is like do the tail expansion. So this tail expansion of the F, like each time you want to do my evaluate, you get in the tail expansion in this way, and when we average out, because the sine signal here is being like disappeared during the entire period. So what is only left now is like the higher moment, the fx will disappear because it's a sine omega t, and only the sine, the gradient power left. So that's the average analysis like for those systems. So now this is about extremely seeking control. And what I'm going to show is like now let's compare the zeroth-order method I talked about from the optimization community. So this is a discrete time, this is a continuous time. That's one difference. I guess you guys probably already can recognize the similarity between the two. So the problem signal here is deterministic case signal sine, and this is the random signal. And the problem magnitude, this is the A, and this is R. And control signal K, this is step size theta. Right, so you look at here, it's almost 1-1 mapping. But I think they develop from like the different intuition. This is about in expectation. I want it roughly be the gradient descent. This is the on average. I want it to be the gradient descent, like the average over the period. So why putting it this way? So now let's look at the block diagram. The block diagram, I want to using the similar block diagram for the single point discrete time method. Right, I have the state. Now I do the random perturbation, putting that in, perturb the system, and getting the observation, and times this signal, and that's my gradient estimation. So now this is my grade, like single point zeroth-order method. You see, like that's how exactly we can use the block diagram. So why I'm doing the block diagram? So this is like when we check in the extremely seeking control textbook, people alone say, okay, we go ahead to use, and we notice there's some unpleasant trend dynamics happening from the dynamics, and then we want to like improve it. So what people did is people add high pass filter and low pass filter in those sides. So the low pass filter in the high level kind of makes sense. Yeah, I want to kind of get rid of those high frequency signals that are too much perturbation. And then what happened for the high pass filter? So, and what's the reason for it? So typically the high pass filter is actually going to wash out some DC component. It's helping me to getting a better gradient estimation. And low pass filter similarly is actually also more some high frequency signal help me getting the better gradient estimation. So I have one slide kind of explaining like mathematically why the high pass filter and low pass filter is helping. So I will skip the like math from here given the interest time. So, but basically what I want to say is for the extremely seeking control, because we already put in the block diagram with dynamical system, we can just go ahead and think about filter design. You can even go higher order. This is the first order filter. You can go higher order to making like shape the dynamics you want about the learning dynamics. So that the question we ask, can we borrow the idea of the high pass, low pass filter for our single point zeroth order method for the machine learning algorithm in the discrete time? And we put it into that, and the message is yes. I will tell you the outcome. So, and we actually also found the interpretation, what the interpretation for those kind of high pass, low pass filter in the discrete time domain. What this shows, like this is the vanilla single point method, X gradient estimation single point. So we end up has a high low pass filter. We definitely like some deviation to making a clean form. So what is interesting is the high pass filter will corresponding to some residual feedback. So still for each time only do 1 point evaluation, but rather than just throw the old information away, I'm keeping it. And when I'm going to evaluate my gradient, I'm going to using the changes of the Fk and Fk-1 as my information to estimate my gradient. But this is different from the finite difference. This is like through this kind of high pass filter way. And the low pass filter had another nice interpretation. It's kind of becoming like a momentum algorithm. The low pass filter adding momentum to my learning dynamics. Putting them together, this is actually coming from the high pass and low pass filter. And I can show you how we actually getting the result. And like we had a block diagram. What we did, we just throw those high pass, low pass filter into the block diagram. So for the high pass filter, right, this is a kind of continuous way to write it down. We just like do those simple discretization and to see what exactly will coming up by this derivation, then the residual feedback naturally happen. And there's also some parameter can help us to tune the parameter. So like for example, the beta will tell us like how much you should trust about the residual feedback, or sometimes you should just like throw away, like becoming your original vanilla single point zero estimator. And depending on the F structure dynamics, the different parameter can be chosen. And for the low pass filter, similarly, what we did is like by looking at this block diagram together and like writing down what is the discrete time method for this one, then we naturally got a nice clean form, and that turns out to have a momentum. And again, some other parameters people can go ahead to tune. So like for the math details I refer, like you guys can read the papers to see how we really derive everything, like the paper is on archive. So putting together, I want to say, when we found this like interpretation, we are very exciting, but definitely I think a lot of people already know the optimization, different kind of optimization method can be like, we can interpret those methods like the using like momentum and like filter language to think about like PID can have some optimization interpretation. So when we put it this way, we actually found it very exciting because first of all, for this the residual feedback, some people from the learning side, they also recognize if they do the single zero order method, rather than do that, we can add in something and they call it this residual feedback. So that we actually just using their name, hey, this is actually the residual feedback from our interpretation, it comes from high pass filter. And the momentum is like have been used in optimization field for like almost many different problems, like adding momentum here, there, and you probably can better like improve the method. Now about the intuition, like the high pass filter, the residual feedback, what is actually really doing? It's kind of doing the variance reduction. And the low pass filter, like since it's integrated the momentum, what it's been doing is actually accelerate the method. So that's like in together, that's the actually first time I've been seeing the once I doing the block diagram, it's really helping me to really go ahead to derive some new optimization algorithms in a very natural way. So now about performance guarantee, again, this is similarly, I think our theoretical guarantee is more conservative compared with the real performance. So this is a single point estimator that performance guarantee we have from our paper. And this is the benchmark. So I want to highlight, so why do I mean this as benchmark? So this is a scenario if I can do determinist case, 2-point finite difference estimation. So you can imagine if I can really do the finite difference, so it can perform better because the finite difference can be a much better estimation of the single point. So this is the question people ask, like, can the single point perform as well as a 2-point estimator? So, and we look at the benchmark, the vanilla single zeroth order method. So this is about guarantee they have. Is like conversion speed is 1 over epsilon to the cubic, which is worse than our result, like, but our result still worse than 2-point estimator, but it's like already improving the confidence rate to a great degree. And if we only had the residual feedback, right? If you can remove the high pass filter or remove the low pass filter, again, this is becoming worse. And the D is the dimension of the problem. So the X dimension is D. So for those single point estimator, dimension is very important because if you have a higher dimension, you probably need to explore more about all the directions. And by doing the high pass and low pass filter, like it's almost right now, it's kind of close to the 2 point, but there's still room for improvement. But I want to show you some numerical result. We compare with different type of methods. So the figure got very busy. So the blue line, this is our high low pass single point estimator. And the red one, this is a 2 point. So you can look at here, right? It's much better than other method if I don't add in the high and low pass filter. And it's very close, like roughly, like for this one is very close. And this one is very close to the 2 point estimator. So this is one open questions for this work, like this kind of the conclusion for this side. So one future work we are right now thinking about is we did the simplest way of the like first order high pass filter, first order low pass filter. So now if I really view those problems in terms of the filtering language, right, I can go ahead to design more complicated filters, right? That's the like higher order filter will bring benefit or not, and how. So those are some work we are currently still thinking about. We don't have a like answer for that yet. So with that, almost I'm going to conclude my talk. It just probably someone will be interested why we don't do the natural. We actually had a natural method in the other paper. Something I want to highlight is a gradient method. If you do the natural method itself, it's not robust to the measurement noise, even the F is strong convex. So they put in this is a natural method in the continuous time. And if we just do the simple thing, this is just like a minimization of like X squared. So we just add the noise on the gradient evaluation. So this is how the dynamics is going to be look like. And think about our zeroth order method, because I never really have the true gradient. I always have a noise. That means in practice, the natural method is not going to work for the application I was talking about. We have one way to make it better is we did the collaboration with Jorge. I think we also interviewed Purdue last semester. So this is the work we work together. So we try to figure out a way how can we robustify this method. So the way we're going to robust it, we had like putting into the hybrid domain, we had like the some one parameter is such as a t. 3 over t is a problem that's caused instability. So we had one way to regularize this problem and to making sure the method is going to work. So if you're interested, feel free to read these 2 papers and feel free to ask me questions. So with that, I want to end my talk. So like talk about, I think a 2-part story. I wouldn't say we already solved all the problems. Like there's still like more questions than the answer we have been provided. So first is learning for control. We're doing the zeroth order method. And second one, we actually can use a lot of control, like the filtering method to improving the control, to improving the learning method. So one thing I want to say for the zeroth order method is, I think it's a powerful method. If people don't care about guarantee, like people can just go ahead to use it and to see how the performance look like first. Like heuristically, it's a very powerful heuristic method. So with that, I would like to end my talk and thank you everyone.
Thank you so much, Lina, for the great talk. Very interesting work. So I think, yeah, we can now see if the audience have any questions. Feel free to just unmute yourself and ask if you have any questions, or just type in the chat and I can read that.
So I actually had a question. So thanks, for the great talk. So my question is again related to the sample complexity of the zeroth order methods, right? So you were able to use this great idea of high pass and low pass filter to improve the sample complexity. But I was wondering if we know any lower bounds, right? So what's the fundamental limit of performance with respect to the dimension of the decision variable as well as the number of iterations that we need?
Yes. That's a great question. So actually, like when I started looking into the zeroth order optimization itself, I was trying to look at the information theoretical bound. I wouldn't say for the convex function, like people have some result. I think natural, and I think like 2017, there's some people working on it. But in general, like back to the question, like for the single point, you can define the oracle in the way each step when you update, how many points you put in there. So determinist case problem will be easier to achieve, like you understand. And the stochastic one, at least now on top of my memory, I couldn't really think of any paper had a like answer for that directly. This is the best thing we can achieve. Yeah. But that's actually the first question people go ahead to ask. So for example, the 2-point estimator for this guy, if you're not putting the D, so this is almost the same speed as the like smooth convex function. Yeah, so like this is almost, I would say, the like good, like if you're not going to do the additional, the natural, the acceleration version, this is the best one is that being like achieved. But then the additional difficulty, now you have the stochastic and you have the fx like omega, then it's becoming more complicated depending on definition, assumption of the omega.
Yeah, thank you.
Oh, hi now, this is Bing. I think excellent talk. Yeah, I think we can talk about it later. I think just what you talk about robust learning, right? And I think
yes.
you were talk about the truncation for bounded T, right?
Yeah, you mean the first part of work, right? So we did the truncation. Yes, we did the truncation to guarantee stability with high probability. We cannot still say like, hey, probability is a probability 1. No, yeah.
Yeah, and then we do truncation. What's the? Do you have any kind of criteria for you to do what truncation? And we have just see the how do you choose those thresholds?
Yes. So in the paper we have like there's one assumption. One assumption which is critical for right now, at least all the Zeroth-Order method for control that happen everything, is that the one assumption people assume is I will start with a stabilizing controller. Because you look at here, this is a gradient descent method. I will start with a like my control policy K0, then go ahead to K1, K2, K3. So like typically the like at least like our paper and many papers, if they really care about the rigorous guarantee, they were assuming the K0 is a stable controller. So then like for our truncation, what we did is we using the K0 cost, like the J0 as a benchmark of the truncation. But we know that, hey, so if the cost is larger than J0, we already truncate everything. We put in like, for example, 10 times J0. And then those parameters will affect what the probability guarantees that we can really achieve. Yeah, so we have, in the paper, we have like some guideline about choosing those parameters.
Yeah, okay, thanks.
Yeah,
yeah so I think bringing this up because here, right, I'm also doing the just the adaptive robust control theory. It's also just kind of learning and but mainly from control aspect, right? Just learn and control feedback of say whether sense information. You just you can feedback in a very fast way, or with feedback in a slow way is more or less learning. So and it's very interesting that yeah we have a lot of things. Just the not the problem is the perspectives and similar things. Here, when I achieve robust learning, I have to, because we do have the process the disturbances stuff and things.
Yes.
I'm relying on prior known structure, say, for information to condition learning. And I think that's all worry. Yeah, you're here to truncation, right? You have to be based on something. Right? So this the connection. I think we can talk about later.
Oh, that'd be great.
Yeah, other questions we can talk about later.
Yeah, great. I think that's a good point. So I think like if you guys attended Ian's talk yesterday, so you see Ian participated the model-free method, and also then Ian's major work for doing the model-based method, because when we really think about safety and robust, it's really safety. Then for the model-free method, I don't have a clear answer how can we guarantee safety during the learning. It's even like much harder. So we actually went to do the model-based method, because for the model-based method, I have some specific guarantee about the estimated parameter and what error of it, and go ahead to figure out those way to put in some buffer to making sure it's safe. Yeah, that's really a great point. For the Zeroth-Order method, right now I don't have a clear idea how to really put in those safety into those methods yet. Yeah. Okay,
good. Thanks a lot. That's probably something that we can work at.
Oh, great. Thank you. Yeah. Other questions? I like answer questions.
Question I have, Nina, from the first part of your talk on decentralized LQR is, so this problem usually you try to minimize the average cost of all the agents.
Yes.
Is there some way to also ensure that there is not much difference across the agents? Like knowing that each agent's cost is going to be minimized at least to some level, not just on average. Are there any works on that, or yeah, what do you think about that?
I think the problem we are doing right now, like, is average. So one thing, like, people can definitely do the weighted average, right? If someone not important, or like you don't think that you need to worry about that cost, you can put it that away. So that's able to be captured in the framework. But I think the base, like, inspired by the question you asked, is I think some more complex scenario. For example, if some agent has more hard constraint, right? I really want to guarantee like my cost is lower than certain bound. And so for those hard constraints, right now, I don't think the method is able to capture that well, right? Unless I change that cost to be what, like the penalized version, like doing the barrel function version, but then that's kind of the soft guarantee. And I think that probably will be some method to do those kind of like safety for the model free method, is then I can translate those safety constraint to some soft penalty function, and then I go ahead to treat that as a validation problem, go ahead and do it. Yeah, but that will be my answer if I go ahead to working on those problems. Yeah, thank you.
Thank you. Yeah. So if there are no more questions, let me just thank you one more time for the amazing talk. It was great to have you here, and I think you're going to have some meetings with the ICON faculty afterward in about 10 minutes or so. Thank you again.
Okay, great. Thank you, everyone. Feel free to email me for any collaboration and questions.
Thank you.
Okay, great. Thank you.